Okay, so for the last lesson that we're going to cover for this unit, we're talking about factoring special quadratics. Now, of course, a quadratic is anything that has a variable to the power of 2, okay? That must be the highest order within the entire expression. So let's start off, first of all, with a little bit of warm-up to kind of jog our memory on some things that we may or may not have seen recently. So looking at this first piece, we can see that this is a complex trinomial. We know this because the a is not a value of 1. That means that we need to use the complex trinomial strategy. So looking at this, is there anything that we can immediately factor out? There is not, so there's no GCF, so we just have to get to work. So that means that we're looking for two numbers that add to negative 12. And we're looking for two numbers that those same two numbers need to multiply to 4 times 9, which is 36. Well, we can see that the final term is positive, so that tells me that my two signs are going to be the same sign. We see the middle term is negative. That tells me that those two numbers are going to be negatives. So thinking about our terms, 1 and 36 isn't going to help me. 2 and 18 isn't going to help me, right? 3 and 12, no, still not there. We got to keep going. And eventually, we're going to end up with an m and an n of negative 6. Negative 6 and negative 6 for both of them. Okay, so let's decompose our problem, our middle term. So we leave the first term alone, 4x squared. And then the middle term, the negative 12x, is going to become minus 6x, and then minus 6x again. But then we're going to add on our final term, which is a 9. Now we do our factor by grouping. So in the first two terms, we can factor out a 2x. So that means we have 2x sitting here still, minus 3. And then in the next set, we have minus 6x plus 9, so we can factor out a negative 3 on this one. Oops, got a little overzealous there. There we go. So we can factor out a negative 3 here, and then that's going to be a 2x minus 3. So then when we group our terms, we end up with our first set of brackets, which is 2x minus 3. And then we combine our two multipliers to be our second set, which is also 2x minus 3. Well, that we can simplify this even a little bit further, and that just becomes 2x minus 3 all squared. Okay? All right, let's try another one. Let's see if we can get something interesting here. So we want to factor 4x squared minus 9. You're like, well, isn't that about as simple as it gets? Remember, that's not what we're trying to do here. We're not trying to simplify. Now, in order to solve this problem, we see that we have an a of, remember the format, ax squared plus bx plus c. Pardon me, I gotta sneeze. Maybe not. I don't know. Okay. So, pardon me. I guess I did. Anyways, we have an a term of 4, and we have a c term of negative 9. But what about b? There's no middle x term. All that really means is that x was multiplied by 0. So this is the actual expression that we're trying to factor. Okay, so that means that we need to find two terms that add to 0. And they multiply to 4 times negative 9, which is negative 36. Now you might think to yourself, well, I guess that means that somehow they have to cancel each other out in order to add to 0. That means that they have to be the exact same number, whatever we come up with. So let's try this. We want to find two numbers, so m and n, whatever ones we actually come up with. So 1 and 36, no, they don't match. What are the two numbers that match that would get us to 36? Well, that's 6. Okay, so let's do 6. Now this is a negative. So that means that they need to be opposing signs. So that means we're going to have a 6 and a negative 6. 6 plus negative 6, that's 0. 6 times negative 6, that's negative 36. Works perfectly fine. So we decompose. So we have 4x squared, and then the 0x gets decomposed to plus 6x minus 6x minus 9. Now, pull out what we can here. So from the first two terms, we can pull out a 2x. So we can factor out a 2x. So we end up with 2x inside and a plus 3. Okay. And then in the next one, we can factor out a minus 3. And we end up with, again, 2x plus 3. So we group everything together. So we have our two sets of brackets. They're our first term. We have 2x plus 3. And our second term is 2x minus 3. Those are not the same, so we can't make them a square this time. This time, the only thing that differs here is that positive and the negative. We've seen these things before. If you go all the way back to 3.1, we learned some shortcuts. And if you remember what those shortcuts were, we were basically saying when we have an expression in a certain format, then we can simplify that and expand it to its expanded form in one step. So the expressions that we saw, or the shortcuts that we saw, were like this. We saw if we have a plus b, and that whole thing is squared, we can expand that in one step. That's supposed to be a b. We can expand that in one step to a squared plus 2ab plus b squared. So we can go that direction in one step. In this case, this is expanding and simplifying. Now, that actually worked the opposite way as well in terms of like we could use positive or negative. If it was a negative sign, then it'd be the same thing, but it'd be minus 2ab. Okay. What this is telling us in this lesson is that, hey, if we see this one, the one on the right, we can actually go the other way as well. This is an equal sign, which means it's balanced. It goes in both directions. So if we're going this way, we're factoring. If we're going from the factored version over to the other side, we're expanding. So the shortcuts work in both directions. Now, similarly speaking, we saw another one. We saw, hey, if we see a plus b times a minus b, then we can shortcut that thing to a minus b all squared. So again, we can expand it into, oops, I messed that up. That's not a minus b all squared. I got ahead of myself here. Pardon me. That's going to be a squared minus b squared. I apologize. A squared minus b squared. So it means that we can expand it to this form, or we can start on the side on the right and we can factor it into the form on the left. Again, it's the same idea. It goes both directions. Now, all we're doing today is we are going to demonstrate those same properties going from the right to the left. So we're going to factor it. So what we're saying is, if we see something in the expanded form of a squared plus or minus 2ab plus b squared, in one step we can factor it to a plus or minus b squared, where the signs will match based on the sign of b. Okay, a plus becomes a plus and a minus becomes a minus. All right. This actually goes by a very special term. When we see this, we call this a perfect square trinomial. A perfect square trinomial. Okay? It means that we have a plus or minus b all squared. It's a perfect square. Now, the one below this one is actually called a difference of squares. What does the term difference mean? It means subtract. So we can see the solution here is this square minus this square. So it's a difference of squares. If we see this, we can immediately factor it to the term we see on the left, a plus b times a minus b. Okay, great. So our goal is always to say, we got to recognize the thing on the right for what it is, and then immediately factor it to the thing on the left in one step. So in expanding these special cases, the shortcuts can be quite a bit more efficient, as it says here. All right, so let's give it a go. We're going to start off with the perfect square trinomial. This is probably a little bit more challenging to actually recognize and see. The warm-ups that we did up top actually solved this problem and showed us everything, but let's try and do it in a single step. First up, to recognize a perfect square trinomial, what we need to do is we need to look at a lot of pieces. Notice that the first and last term are perfect squares. They have to be. And what I mean by that is that you can take the square root of them and it comes out to a nice clean number. So for example, 4x squared comes out to 2x. That's a perfect square. right? But 3x squared, that is not a perfect square because the square root of 3 is not a nice perfect number. Negative 9, that's also a perfect square. We can take that and get the square root, we can get 3. Okay, so those are perfect squares. So the first and last term have to be perfect squares. All right, now the next piece. To factor a perfect square trinomial, we have to consider the square root of the first term, which is a, okay, and the square root of the last term, which is b. Let's do a little bit of highlighting here. So we're trying to get the square root of the first term, a, and the square root of the second term, b. Okay? Pardon me. Now, the trickiest part is the next piece. We have to check to see that the middle term is the equivalent of 2ab, where the sign stays the same. Okay? 2ab. That you have to try and do with mental math. You can do it the hard way and the long way, but you're going to find that you're going to take a long time to do this. So what we're going to do is we're going to create one set of brackets raised to the power of 2. We see that the solution is over here. So one set of brackets raised to the power of 2, where the two square rooted terms are separated by the sign of the middle term. Now that sounds super duper confusing. So let's give it a try so you can actually see what we're talking about. So this first term, this is a, right? And this last term, this is c. And we have b inside of here. So the square root of 4x squared, what is that? That's 2x. The square root of the last term, 9. That's 3. You notice that we're ignoring the sign for now. The sign of the middle term, that's a negative. And that's all I need to know in terms of information of what I need to do to solve it. However, I still have to verify that I can actually do this. So let's think about this. If we have 2x and we have 3, if we multiply those two together, we get 6x. So that's our AB, or sorry, our AC, okay? No, our AB, I apologize. Something is off there. No, that's right. So if we do 2x times 3, we're going to end up with 6x. Now, if we double that, we end up with the 12. So that's how we get that's how we verify that this actually works. So let's try this out. So that means that we're going to take the first term, which is 2x. We're going to take the last term, which is 3, the square root of it. And then we're going to use the sign from the middle term. Now, if you multiply this out, and expand it, you're going to end up exactly where we started. Okay? So let's try that out on a few of these below. Now, of course, as always, the first thing it's telling us is whenever you're factoring, always look for the greatest common factor. If you don't do that, you might end up doing a lot more hard work than you think. So let's give that a try. Alrighty, so fully factor, always look for your GCF first. Do we have a common factor here? We absolutely do not. So now we have to check to see whether it satisfies the perfect square. Now we know that the perfect square, the square root of b squared, that is the square root of b squared, that's going to give us b. We know the square root of 100 equals 10. All right, so those are perfect squares. So that part works out. What about the middle part? So to get the middle part, what we need to see is if we multiply our a and our b here, okay? If we multiply our a and our b, so our b times 10, that gives us 10b, and then double it, we get 20b. So that matches as well. Okay, so that means we can use the shortcut. So in order to use the shortcut, a set of brackets with a square, the sign is going to match the sign of the b term. And then we simply put in our square roots. So the first one is going to be b, and the last one's going to be 10. And that's it. Let's look at the next one. So this one, there actually is a greatest common factor, which is a 3. Okay, so we can factor out this 3 first. And now we have d squared minus 6d plus 9. Okay, so we look for perfect square. Is the first term a perfect square? Yes, that's D. Is the last term a perfect square? Yep, that'd be 3. No problem. Is the middle equal to 2AB? So if we multiply D times 3, we get 3D. And then if we multiply that by 2, we get 6D. So yes, it will work for this. So we're going to leave that 3 alone, because all we're really factoring here is the brackets. And the result of this brackets, we square it, and we end up with D, take the sign from the middle, minus, and the square root of the last term, which is 3. So we have 3 times D minus 3 all squared. Okay. Same process. Can we factor out anything from this last one? I don't know. Maybe. So the square root of the first term, that's 5a. The square root of the last term, that's 8. Okay, so those are both perfect squares. What about this middle term? Is it equal to 2 times these values? 8 times 5a, that's 40a. Times 2, yep, that's 80a. So that does work. So it's 2 times 5a times 8. There we go, 2ab. So that means our final answer is the square root of the first term, which is 5a. Use the sign from the middle, and then the square root of the last term, which is 8. And we square it. And that's the whole thing. Let's keep going. So the next one, do we have a GCF? Yep, we absolutely do. We can divide everything, this one by 2. Can we divide the last one by 4? No, we can't. So it looks like our GCF here is just a 2. So we take a 2 here, and now we have, this comes down to 4n squared. There we go. Minus 20n plus 25. Great. So now we want to factor out the middle set. So first thing I'm going to do is look for my shortcuts. Otherwise, I'm going to have to use the complex trinomial strategy. So is the first term a perfect square? Yep, the square root of 4n squared is exactly 2n. The last term, is it a perfect square? Yep, the square root of 25 is 5. Is the middle term equal to double the product of those two numbers? So 4n squared, that's 2n, multiplied by 5, that's 10n, multiplied by 2, we get 20n. So yes, we can use this. So we have 2, and then we're going to have our set of brackets that are going to be squared. We're going to have 2n, we use the sign from the middle, and the final term. 2 times 2n minus 5 all squared. Same idea for the last one. Do I have a greatest common factor? I do not. That does not work out very well. So we got to go the hard way. Is this a perfect square? 9y squared. Yep, that's going to be 3y. How about 49? Yes, that's 7. So the first step checks. So if I take my 3y and I multiply it by 7, I get 21y. Now double it, I get 42y. So it does work. So I can use it. Okay. So the square root of the first term, 3y. Use the sign from the middle and the square root of the last term, which is 7, and the whole thing is squared. Okay. Last one. We have x cubed minus 18x squared plus 81x. I don't have any coefficients that can be factored out, but I can factor out an x. So let's do that. And now we have x squared minus 18x plus 81. All right. So this would be a simple trinomial if we had to factor it like that. But let's see if we can use our shortcut. The square root of x squared, is it a perfect square? Yep, it's just x. Square root of 81, is it a perfect square? Yep, it's 9. So if I take 9 and I multiply it by x, I get 9x. Now double it, I get 18x. Okay, so both parts check out. So that means I can use the perfect square shortcut. So we have x, and then we're going to use the square root of the first term, so that's just x, the sign from the second term, and the square root of the last term, 9. And that whole thing is squared. So that is perfect square trinomials. Let's highlight that just so we can see it. Perfect square trinomials. So those ones are probably the more complicated. Now let's look for difference of squares. Difference of squares is much easier to actually work with. The solution is just a little bit longer. So a difference of squares. To recognize a difference of squares, there must be What are we looking for here? Yeah, make sure my notes match. There we go. So a difference of squares, remember what it looks like. It looks like this. A squared minus B squared. That's what we're looking for. So to recognize the difference of squares, there must be two terms that are both perfect squares, which are separated by a negative sign, a minus sign. That's why it's called a difference of squares. So consider the square root of the first term A and the square root of the second term B. So we're trying to find the square root again and of A and B, just like we did last time. Now once we have this, we're going to create two sets of brackets where A and B are the first and last term in each set of brackets. And then the signs are just going to be opposite of each other. So this is probably the easiest one to see. So if I have 4x squared minus 9x, 4x squared, yep, that is 2x. Square root of 4x squared is 2x, perfect square. 9, square root of that is 3, also a perfect square. So that means that I can use the difference of squares strategy. So the square root of 4x is 2x. Square root of 9 is 3. We're going to place the opposite signs in each set of brackets. And now we just put A on the first term and B on the second term. So A here is going to be 2x. And then B is going to be 3. And then over here we have 2x and 3 again. And that's it. So we just got to make sure that we can use it. But as always, find a greatest common factor first, if there is one. No greatest common factor in this first one. So is B squared perfect square? Yes. 36. It goes down to 6. So yes. Two sets of brackets. So B is going to be the first term in each one. 6 is going to be the second term in each one. And we just have opposite signs. And we're done. Let's look at the next one. No greatest common factor again. So are they perfect, or are each term perfect squares? 5D and 8. Yep, works out perfect. So we're going to have 5D in the first term plus 8, and then 5D in the second term minus 8. Okay, let's go to the next one. Let's see if we can factor out a perfect square. No, don't you have to worry about it though. Why don't we have to worry about it? We can factor out a 2. That's going to give us 2a squared plus... No, we can't even factor it because 81 doesn't divide by 2. So can't do that. Can we factor in any other way? There's no greatest common factor. And there's no perfect square because we don't have a middle term here. So there's no 2ab. So what is the issue here? We can't use difference of squares either because this is not a minus sign. So in this case, we actually have a term that is not factorable. So it's not there's not a difference here. So therefore, not factorable. It does happen. Pardon me. Okay, let's go to the next one. Can we factor anything out here? Yeah, there's a greatest common factor. We can get rid of the 2. So let's factor out a 2. So that means we have 25. Oops, 25. Oh my goodness, let's erase that. Let's try this again. 25 minus n squared. Leave the 2 alone. It's all on its own now. Now 25 minus n squared. 25 is a perfect square. Square root of that is 5. Square root of n squared is n. So we're good. So we can just use it, and we're minusing. So that means we're going to have 5 plus n and 5 minus n. Factored. Go to the next one. Can we factor anything out? Nope. No greatest common factor. Are they perfect squares? Let's see. 4y squared, that's perfect square is 2y. Good. And the square root of 1 is 1. And they're both being minused? Yep, we can use it. So we're going to have two sets of brackets. And the first term is going to be 2y. And we're going to alternate the signs. And this is going to be a 1 and 2y minus 1. Continuing. Ooh, this one's interesting. This time we do have a difference of squares because our second term, the square root of y squared, is just y. We are subtracting. What is the square root of the first term? You got to treat that whole set of brackets as one term because the whole thing is what's being squared. What's the square root of x plus 3 all squared? It's just x plus 3. That's a perfect square. So that means we can use difference of squares. So that means we have a couple sets of brackets here. We're going to use square brackets here. So our first term is going to be x plus 3. X plus 3. And then we're going to add on to that the square root of our second term, which is y. And now we have another set of brackets, which is going to be x plus 3 again. This time it's going to be minus y. And now we're just going to simplify our expressions a little bit. So we have x plus 3 plus y. Nothing's really being combined here. That x is pretty terrible, so let's fix that. Nothing's being combined, so I can just rewrite this. I'm going to rewrite it as x plus y plus 3. I'm just going to keep my variables together over there. They don't have to be. I'm choosing to be. And then the next one, x plus 3 minus y. X minus y plus 3. Okay. That's that one. There's nothing else to really do here. This one's not as nice, but it's still doable. What is the square root of m squared over 9? We have a difference, so we just got to make sure that these are perfect squares. What is the square root of m squared over 9? Is that a perfect square? Well, this is the equivalent of taking the square root of m squared over the square root of 9, which is equal to m over 3. Oh, okay, that works. That's a perfect square. What about 1 over 16? 1 over 16, we want to see what the square root of is. So again, we have the square root of 1 over the square root of 16. Well, that's 1 over 4. Again, we have a perfect square. So this is going to be our a term, and this is going to be our b term. So we can use that. They're being subtracted. So our first term is going to be m over 3 plus 1 over 4. And our second term is going to be m over 3 minus 1 over 4. And there we go. Now we can leave it like this, and that's perfectly fine. Or you can take it one step further if you wanted, and you could find a common denominator and add those things together to simplify the terms themselves. It's completely up to you. This is fine, and you can leave it just like that. However, if you wanted to take it one step further, that means you're going to find a common denominator of 12 for each one of these sets of brackets, and it's going to look like this. You're going to end up with 4m plus 3 over 12. 3 is pretty terrible. And over here, you're going to end up with 4m minus 3 over 12. I wouldn't take it any further than that, because at that point you're going to start making life more difficult for yourself again, because you're going to end up foiling and expanding, and that's not what we want. Our job is to factor. Keep it simple. Alrighty. We look again. Now we have x to the power of 4 minus 8x squared plus 16. Do we have a greatest common factor? We don't. Do we have a perfect square? Well, not so much. So what can we do here? What can we actually, sorry, a difference of squares. In this case, we actually can't factor with a difference of squares, but can we factor with anything else we've learned? We do actually have a perfect square, because we can see that the square root of x to the 4th is going to be x squared. We can see that the square root of 16 is going to be equal to 4. Now, does the middle term equal to double the product of these two terms? So the product of these two terms is 4x squared. Now, if we double this, we end up with 8x squared. So yeah, we actually have a perfect square situation here. So that means that we take the first term, which is x squared. We use the sign from the middle, which is minus, and the square root of the last term, which is 4. And this whole thing is squared. Now, are we done? Well, let's find that out. If we multiply this, if we put that square through both pieces, what we end up with is this. We end up with, how do I want to say this? Well, actually, let's leave that square root alone. If we're looking inside, we can actually see that that actually is a difference of squares. X squared minus 4. Oh, so this is a perfect square. But by taking that perfect square, we've decided that we're not actually done yet, because inside this set of brackets is actually a difference of squares. So we're going to leave that square alone. And inside this set of square brackets, I'm going to do my difference of squares. So I take the square root of the first term, that's just x. And then we're going to add and we're going to subtract. And the square root of the last term, which is 2. Now from this point, we can now put that square into both elements. So we end up with x plus 2 squared times x minus 2 squared. Holy smokes, that is quite the factor job. We had to recognize the fact that we had both a perfect square and a difference of squares. Almost missed it myself on that one. Okay, let's look at this last one. Oh, what do we got here? We don't really have much to work with. Now, some of you are going to look at it and say, well, could we factor by grouping? Because we got 4 terms. That makes sense. That should be your first train of thought. You might also look at the fact that last one there is actually a difference of squares. That would be 3 plus 5y times 3 minus 5y. That's not necessarily wrong. But then we have to deal with the fact that we have this x squared minus 6x sitting over here. And that's not really helping us. Is there anything else we can see? Well, I can see that if we group these 3 terms here, these first 3 terms, that we actually have a perfect square here. Not a difference of squares. We got a perfect square. The first term, square root of that is x. The last term, the square root of that is 3. 3 times x, that's 3x. Double it, we get 6x. So that means we have a perfect square here. So let's try that first. And then we're just going to leave that minus 25x or 25y squared all on its own. So if we do this, that means that we're going to get x minus 3, because we use the sign. And from here, we're going to end up with, that's going to be squared. Yeah, x minus 3 squared. So, and then we have our minus 25y squared. Oh, look. Now we had our perfect square. Now we've just created a difference of squares. We have a square term here that can square down to a nice number. And then our 25y squared also goes down to 5y. So now we've created a difference of squares. Okay, so we have a set of brackets. We have a second set of brackets. And in the first set of brackets, we're going to have x minus 3. And we're going to add on to that 5y. In our second set of brackets, we're going to have x minus 3. And we're going to subtract on from that 5y. Can we do anything from there? No, we can't. We're done. So x minus 3 plus 5y and x minus 3 minus 5y. I could rearrange it if I wanted to, and that would work just fine. All right, we're going to finish this off with a problem. A word problem. This is going to be a common type of problem you'll see in practice work as well as assessments. So make sure that you have a good idea of what we're doing here. So find an expression for the shaded area. So we have this big box that is shaded in, but we have this white box inside of it. Okay. I want to find an expression for the shaded area only for the following shape. Then we're going to factor the expression. Okay. So first up, how do we know the area of just that shaded part? Well, that area is going to be the area of the large rectangle, or the large square, I guess, minus the unshaded area, so the small square. So since we know that, let's put this to the test. The area of any square is the side squared. So that means it's going to be 2x plus 3 squared minus the internal area, which is x minus 1 squared. So there's our expression. Now we need to factor it. Oh, look, a difference of squares. That is a difference of squares. So each one of those is a perfect square, and we're subtracting them. So that means we're going to create some brackets here. We're going to need some extra sets of brackets. Instead of using that round bracket, we're going to use a square bracket. So for the first set, okay, now we know we're going to have the square root of the first term, which is just 2x plus 3. And we're going to add on to that the square root of the second term, which is x minus 1. Okay. And now the second part is 2x plus 3 again. And we're going to subtract from that x minus 1. Now we have to do the work. 2x, we're going to combine as much as we can. 2x plus 3 plus x minus 1. And over on the other side here, we have 2x plus 3. But that minus applies to both of those terms. It gets distributed. So that means it's going to be minus x plus 1. Careful. And now let's combine. 2x plus 3, we can't combine that. We can combine the two x's, so we end up with 3x. 2x plus x is 3x. And then 3 minus 1, that's going to give us 2. Oops, I should probably put an operation between there. 3x plus 2. What about the next one? The next one, 2x minus x, that's just x, and 3 plus 1 is 4. Well, there we go. That is going to be our final factored expression for our shaded area alone. That's where we're going to stop it, okay? So we've learned, if we summarize everything, we learned how to expand and simplify. Multiply, 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 multiply. Then we spent the entire rest of the unit reversing that process. So we have our expanded simplified form, but now we're going to bring it back into its factored form. And we learned a number of different strategies. The first strategy was called common factoring, where we find the greatest common factor and divide it out from each term. Then we learned factoring by grouping, where we grouped two binomials together, and we ended up pulling out one for the first term, and then combining the multipliers of those brackets to get the second term. Okay, and along the process, we learned some shortcuts for expansion and some shortcuts for factoring as well. But before we do that, let's talk about simple trinomials. Simple trinomials are any trinomial that is in the form x squared plus bx plus c. Now, keeping this in mind, that means that we could factor those things as long as that a term is not there, which means it has a value of 1. And to do that, we need to find two numbers that add up to b and multiply to c. And then we can create our final solution from there. But sometimes a is not 1. Sometimes it's something else, in which case we call that a complex trinomial. In that situation, we're going to use a strategy called decomposition, which is where we have ax squared plus bx plus c. But this time, what we're going to do is we're going to find two numbers that add to b again, but this time they're going to multiply to a times c. And then whatever terms we find, those, instead of just being our middle term, those terms are going to take the middle term and decompose into those values, creating 4 terms. And from there, we're going to continue factoring by grouping. And then finally, today's lesson was all about recognizing perfect squares, which means that we have something in the form where we have 3 terms, 3 terms of our trinomial, where the first and last term are perfect squares, and the middle term is the equivalent of 2 times the product of those perfect squares. And that will give you that value. If that's the case, then we can simplify it and factor it in one step. The other thing we learned was something called a difference of squares, is where we have the subtraction of 2 perfect squares. And that creates another simple result in a single step. So that's a summary of everything we got. Hopefully it's clear, but if it's not, that's where the practice work comes in. That's where the extra help comes in. So make sure to take advantage of all those opportunities. Thank you.